we present a computational framework for modeling and optimizing rigid assemblies using cone joints. In practice, an assembly with planar contacts is often unstable. An assembly with perfect tenon joint is hard to assemble. Our cone joint can provide a balanced solution that ensures the structure having both stability and assemblability. Using the two-part assembly as an example, our method first analyzes the joint's motion space, which consists of all possible infinitesimal rigid motion to take the green part out from the blue part without collision. To compute the motion space, we sample the curved contact joint to obtain the contact points and contact normals. Using the contact point R and contact normal N, we can compute the generalized normal and the generalized normal space. The motion space is then all possible motions that satisfy the non-penetration constraints. Equivalently, motion space is the dual cone of the generalized normal space. For this 2D joint, its generalized normal space is a curve in 3D, which can be further simplified by its convex cone. The conic section is used to visualize the 3D cone. The motion space is also a 3D cone, which can be represented by its conic section. By changing the joint's geometry, the motion space and generalized normal space are changed accordingly. Given an unstable input assembly, our algorithm first determines the optimal motion cone for each part contact. Here, we show the optimization process of the purple joint. Then, our algorithm iteratively finds the geometric realization of each joint to match its target motion cone. Please refer to the paper for more detail.